Right, question 15 here says change cosine of phi minus the sine of phi all squared into 1 minus 2 times the cosine of phi times the sine of phi. That's that Greek letter phi, by the way, there. So I started off writing proof and restate that left side. And I'm going to do that thing that it actually says to do. I see that squared up here, so I'm actually going to square this. Okay? Write out that this is going to be cosine of phi minus the sine of phi times the cosine of phi minus the sine of phi. And I don't need to justify that step right now, right? That's just squaring it out on that right side. And I'm actually going to do this, right? That I can't just distribute the square across this. It's not cosine squared minus sine squared. It's cosine minus sine times cosine minus sine. And I need to do the whole first, outer, inner, last. So this becomes cosine times cosine first, the cosine squared. Cosine minus sine is just minus cosine times sine. Negative sine times cosine, that's another, I'll write it in this order. It's cosine times sine, it's negative. My order, it doesn't matter, and it'll be convenient to have it like this. And then a negative sine times a negative sine will become a positive sine squared. Again, nothing I'm really justifying. This is all algebraic steps, so that's not my expectation. But now, I'm going to rearrange this a little bit. These can combine, right? Negative cosine times sine, negative cosine times sine. That's just, I have two of them. Minus 2 cosine times sine. I bring this sine squared out front with the cosine squared, so I have cosine squared theta. Nope, I shouldn't write theta. This should be a phi the whole way down. Keep it consistent. Plus sine squared phi minus that. So I'm really just combining my terms and rearranging. But now this, cosine squared plus sine squared, that is 1. I have the minus 2 cosine times sine, and hey, that's what I wanted to show. So I finish it off by justifying. Really the only property I used in this whole proof was that Pythagorean property that I write after I take the step to do that, and then I say, therefore, cosine of phi minus the sine of phi all squared is equal to 1 minus 2 times the cosine of phi times the sine of phi, and that's what I wanted to show, QED. And the next one that we suggested was to take tangent n plus cotangent n quantity squared, turn that into secant squared n plus cosecant squared n. So I'm going to start by just restating this, write proof, have this quantity squared, and just like the last one, I'm actually going to square it. And I'm going to do tangent n plus cotangent n times itself. And again, I'm going to do tangent times tangent, which will make tangent squared. I'm going to do tangent times cotangent, which I'll write cotangent n, and then again plus cotangent times tangent, which I'll rearrange the order here, and then last cotangent times cotangent is cotangent squared. I could combine these two things, tangent times cotangent, or right away I could say this is tangent squared, and this is just 1 because of that quotient property that we have. That tangent times cotangent, they're reciprocals of each other, so they're both equal to 1. And this one too I can change to just 1 plus cotangent squared n. And I'm going to do that because now these are just Pythagorean properties. I don't want to really combine these and make a 2, I'd just have to split it back up. But tangent squared n plus 1, that is the secant squared. And 1 plus the cotangent squared, that is just the cosecant squared n, and I would need to justify that step. Pythagorean property, and right away, that's it. I did that distribution, my reciprocals make 1 here, and I'm left with what I wanted, and I finish it off. Therefore, the tangent of a thing plus the cotangent of a thing squared, it's the same as the secant squared of that argument, that thing, plus the cosecant squared. And that's what I wanted to show, QED. My next one's number 19. I want to show the cosecant squared of x minus 1 divided by the cosine of x is equal to cotangent x times cosecant x. This one involves some other functions that are not the sines and cosines, so it's a little more interesting. But right away, start by restating this, and I have this top thing, that's that difference of squares, that, yeah, cosecant squared minus 1 is just the cotangent squared. So immediately, I think Pythagorean property because of that cosecant squared minus 1, and I'm going to write that there and justify it by saying that's the Pythagorean property that lets me say that. From here I have a few different ways I can go, and they all involve stacking fractions on top of each other. Right? That cotangent squared I might split apart right away. Say this is cotangent x times cotangent x, and I'm doing that because I want to get the cotangent x up by itself right away. So that means that, well, cotangent x over cosine of x, this must just simplify down to cosecant of x. I want to get that cosecant of x. I could split this apart here too. There's nothing really justifying there. Cotangent squared is cotangent times cotangent, and this also is just algebra that I can break this apart here. And I might change all of this. I said when in doubt change everything to sines and cosines, but I want to get a cosecant, and it's just one term. I think it's safe to change everything instead maybe to secant and cosecant. So this cotangent x is going to stay out front. My cotangent quotient property is that cotangent is cosecant over secant. And cosine is 1 over secant. And I need to justify this. I can do them both in one. I'm using the quotient property for the numerator and the reciprocal property for the denominator here. So I justify both of those that way. Now I have this stacked fraction that I want to change. Say this is going to be, I'm going to keep the numerator the same, cosecant over secant. But I'm going to change that division to multiplication and multiply by the reciprocal of that denominator. And now my secants are going to cancel out. Right? There's nothing really here. Keep, change, flip if you want. Right? Multiply by the reciprocal of the denominator when you are dividing by fractions. My secants are going to go away, and I'm left with cotangent x times cosecant x after those are just gone. Over 1, who cares? And that's what I wanted. I wanted to show that this cosecant squared x minus 1 all over cosine of x was equal to cotangent times cosecant. Get my little therefore, and that's what I wanted to show. Number 21 is very similar to number 19. It's basically the exact same proof, but with secants and sines and tangents instead of cosecants and cosines and cotangents. I'll do it a slightly different way, so you have another I on it. It's going to start the exact same though. That secant squared minus 1, Pythagorean property, that's going to become tangent squared of theta all over sine of theta. I justify after I take the step. Now I'm going to maybe just change everything to sines and cosines, as I've suggested doing, right? I want to get a secant, I want to get a tangent, but some people just said, hey, right, I'm in doubt here, let's try to change it to sines and cosines, so let's do that and see what happens. My tangent is sine over cosine, so tangent squared is sine squared over cosine squared. It's a quotient property that lets me do that, and that's still over the sine of theta, and we're still having fractions divided by fractions. I'm just going to put that sine theta over 1 to show what I'm about to do next. That if I have a fraction in the numerator divided by this fraction in the denominator, again, you'll notice I make this line a little bit bigger, longer, so that I know that I'm keeping numerator and denominator separate. So I'm going to keep my numerator, change my division to multiplication, and flip my denominator so that it's now 1 over sine theta. Again, no justification needed, just dividing fractions. Keep, change, flip. And here, I know I have a sign here and a sign up top that I could probably cancel out. Right? So I'm just going to cancel this and rewrite this, combine those. I'll end up with sine of theta over cosine squared of theta. That I'm going to split that up too as a cosine of theta and a cosine of theta. There's our bell. That sine of theta is really, it's sine of theta times 1, and I can group this how I want. That I have sine over cosine here that I can group together and call that tangent. I have 1 over cosine, that's the secant. So I'm using 2 properties in one step again. I'm okay with that. Just the quotient for the first part and reciprocal for the next part. And that's what I wanted to get to. So, a slightly different way to do that one. They're both valid, but therefore, start with secant squared theta minus 1 over the sine of theta is equal to tangent times secant, and that's what I wanted to show.